Uh, so if you saw it yesterday, it was a pretty cool deal. The Perseverance Mars lander successfully deployed on Mars, and we'll go through kind of once we get into more forces and gravitational fields, we'll talk more about it. But it was a pretty exciting deal, because the short version is that here's the sun. Oh, there's the sun. Here's the Earth and Mars. And this obviously isn't the scale. So they actually launched this thing back in February. So you had to go through the math of it. You launched from the Earth, but then you had to launch it to Mars. Well, here's the problem: is that Mars is stationary. Mars is moving in an orbit. So it's kind of like throwing a pass to a receiver or kicking a ball to another soccer player. You don't shoot it where they're at. You have to shoot it where they're going to be in 6 months. So so you basically had to aim for a point that Mars was going to intersect at that point. So then even the testing was insane, because the atmosphere on Mars is about 1% of the atmosphere that we have here. And so there's enough that you can deploy a parachute, but it doesn't work like a parachute on Earth because the atmosphere is so thin. So when it hit the atmosphere, it started to heat up, and we'll talk more about energy. So basically, when it hit the atmosphere, it had a tremendous amount of what we call kinetic energy. Kinetic energy is the energy of motion. And you had to go from traveling at about 5 miles per second to stopping in a relatively short amount of distance. And so you had to somehow get rid of that energy. And so because it hit the atmosphere, it started to heat up. And so you lost some of that kinetic energy into thermal energy, because the heat shield began to warm up, and that began to slow it down. And then you deployed the parachute, and that lost even more. And then you had some rockets that fired, and it was, if you look at the distances involved, it was stunning to be able to launch something that far, and then it actually landed within about 30 meters of the desired landing spot. And so if you consider the technological advances in launching a probe from Earth to Mars and having it land with basically within a football field at Mays High School, that's kind of like the analogy. So it's a pretty stunning engineering feat. And I'll send you out a link. There's a cool YouTube video that goes through and explains like the behind the scenes look at all the technology that went into it. So I'll send you out that link. It's about 20 minutes long, but it's a good read. So anyway, all right. So let's talk about the assignment with the graphical edition of vectors, which I thought I had up here, and I do. So let me kind of get you through what's going to happen with the test, okay? So you're going to have, on the test, you're going to have 3 different vector problems that are going to be on the last page of the test. So the first vector problem is going to be like the first assignment that I've sent back to you all. And I'm going to give you a series of vectors, and I'm going to say, oh, draw them tip to tail. So you're going to start with some coordinate system, and you're going to go, oh, here's vector number 1, here's vector number 2, there's vector number 3, boom, draw that resultant, measure that angle. Okay, so that's what the first one is going to be. So make sure that for those of you that are coming into school, take the test. Okay, so hopefully you can come back and take the test. If not, you can take it from home. So, but make sure that you bring a protractor and ruler, because you're going to have to do a problem like this where you can measure things out and measure, do all that good stuff. Okay, so there's that. So the second problem is going to be like number 4 on this. I'm going to give you like a launch velocity, like let's say it might be, I don't know, 60 meters per second at an angle of 50 degrees. And then I'm going to ask you to find the x and y components of that. So again, you have to look at what you have on your equation sheet. So the only thing you have on your equation sheet is how you find sine, cosine, and tangent. Okay, that's what you have in your equation sheet. So you got to realize, oh, this vertical component over here, this y component, is going to be the side opposite of this angle. So that's going to be like 60 meters per second times the sine of 50 degrees. And then get my x component, that's going to be 60 meters per second times the cosine of 50 degrees. Okay? So this is going to be the second problem. Now, and it's going to be a velocity. I'm going to tell you straight up, it's going to be a velocity. Right? But here's one thing. I don't want you to look at this in terms of like a position time graph and go, oh, that's going to be meters and that's going to be seconds. They're both still meters per second because sine of 50 degrees is just a number, cosine of 50 degrees is just a number. So when you multiply that by meters per second, you still get meters per second. So anytime you do stuff with vectors, when you find the components of it, technically known as deconstructing a vector, you still end up with the exact same units. Okay, so don't change those. Now, this one, if you want to make a sketch, you can, but fundamentally on the second one, you're going to use your calculator. Make sure your calculator is not in radian mode before you start the test. Okay? Make sure that you're in degree mode, and that's going to be the second. The third problem is going to be something like number 6 or something like 5, 6, or 7. I'm going to give you two vectors, and I'm going to ask you to find the resultant of it. Okay? So this is this is going to be your exact sequence. The graphical ones, you're going to do one like this when you find them, and the third one is you're going to make a sketch. You're going to draw it out and find your x and y components and all that good jazz. And I promise you, you have to draw this chart. So let's say, for example, you have one like number 7. Okay. Actually, let's start with number 6. So in number 6, this is what I would do. Okay, if I've been doing these longer than you all have been on this earth. If you said, hey, Burkamp, work number 6, I'm going to show you the exact sequence that I would do. Okay, so the first thing I would do is that I'd come in here and I'm going to make a sketch. I'm going to go, okay, hey, I got 5 newtons at 60 degrees. Okay, so there's 5 newtons at 60 degrees. Okay. All right. Now, at this point, I want you to think this through. So you're eventually going to set up a chart, okay, and you have to draw the chart on this test. So I'm going to have 5 newtons, and then you're going to have 10 newtons. 5 newtons and 10 newtons. Here's my x, here's my y. Okay? So, I got 5 newtons at 60 degrees. So I know I'm going to have a positive x and I'm going to have a positive y. This is just off the sketch. Okay? So I know these are both going to be positive values because it's in this first quadrant. At least because this is a 60-degree angle. Which is going to be bigger? My y component or my horizontal component? Y. Yeah, it's a 60 degrees. It's above 45 degrees. So when I do this, I know my y value here has to be bigger than my x value. Okay? Now, then I've got, the next one is going to be at 80 degrees. Okay? So from the end of this is like a whole new coordinate system. Now I'm going to draw 10 newtons at 80 degrees. Okay? So this is going to go up here like this. So there's 10 newtons at 80 degrees. And again, this is just a sketch, so I have an idea of what's going to take place. So now, when I draw that resultant here, okay, just based upon this sketch, I know that my angle has to be more than 60 degrees. So when I get my answer on this one, just based upon a very crude sketch, my angle has to be more than 60 degrees. Now, drawing it like this is what we call this tip-to-tail method. Okay? I get an idea, well, it's going to be a longer vector, and the angle is going to be more than 60 degrees, okay? If you like that, that's cool. Now, the other thing that you can do is draw it as what's called a free body diagram, where you draw all the vectors acting from the center. So if you could do the same viewpoint, and it's like a soccer ball, okay? So Elise is going to kick the ball this way with 5 newtons at 60 degrees. Then maybe Grace is going to kick the ball at 10 newtons at 80 degrees. Okay? So Grace is kicking the ball this way. Elise is kicking the ball this way, okay, at the same time. So you got to figure that ball is going to go somewhere in between these two vectors, okay? Because this is kicking it this way, Grace is kicking it this way. It's going to go somewhere in here, okay? So right away, even if you do this, oh, I know my angle has to be between 80 and 60 degrees. So if you don't get that, then you know you did something wrong. So here's what I'm going to look for, is that you lay out, oh, here's my x component, here's my y components, you find the sums. So like on this one, on number 6, your x component should be around 4, and your y component should be around 14. So when you add up your x components, you should get around 4. Your y component's going to be around 14. Now, here's the most vital thing that you have to do, okay? You want to go and now make another sketch that says, oh, okay, I've got an x component of about 4, and I've got a y component of about 14. Boom, I'm going to find this resultant, okay? So, at this point, you want to do 2 things. You want to use the Pythagorean theorem to find the resultant. And then you want to do inverse tangent to find the angle, because it's a vector quantity. And here's another thing I'm going to ask you on the test, okay? I'm going to ask you, what's the difference between a scalar quantity and between a scalar quantity and a vector quantity? I want to ask you this question, okay? It's going to be at the top of the last page. I'll even tell you where it is on the test, okay? And what you want to use is the word while. You're going to say, oh, a vector quantity has magnitude and direction, while a scalar quantity only has magnitude, okay? That's what you want to look at. All right, so if you just find the resultant, that's just the magnitude, so you got to give the angle that goes with it, okay? So make that sketch. Now, if you look on number 7, number 7 is a little bit more difficult, mainly because of where the vectors are. But again, if you make a sketch, you're going to have an idea of what's going to happen. So on number 7, I got 5 newtons at 100 degrees, okay? So there's 5 newtons at 100 degrees, and then I got 100 newtons or 10 newtons at 200, which puts me somewhere down here. And again, look at this in terms of the soccer ball, okay? Matt's kicking the ball this way, okay? And, I don't know, Kara's kicking the ball this way. So you've got to figure the ball is going to go somewhere in between here, okay? It's going to go somewhere in between here. So just based upon this, your angle has to be somewhere between 100 and 200 degrees, okay? Because if you're kicking the ball this way. And if it's not, then you know you did something wrong, okay? And again, just make a sketch, and it's going to tell you at least a ballpark idea of what your answer is going to be. So on number 7, here's the deal. Because of this being in the 3rd quadrant, so this 10 newton is going to have a negative x component and a negative y component. This is going to have a negative x and a positive y, okay? So even if you do this sketch, when you fill in your chart, you'll at least have an idea of what the signs should be. Oh, negative x, negative y, negative x, positive y. So that way when you look at your chart, when you get done, it's like, oh, hey, does that seem like a reasonable value? Okay. So, like I said yesterday, your answer to number 6, that angle should be in the 70s. And your answer to number 7 in terms of the angle should be around 170. Okay? So there should be about a 100-degree difference between your answer to number 6 and your answer to number 7. Okay? There's about 100 degrees of difference between the two of them. Okay? Grace? Elise? Are we good?
Yeah.
You sure?
Well,
Okay, all right, speak now for everybody, please.
On 5, I didn't get 220-ish on the last one, but I just think I did the math wrong.
Okay, so hold on. Let's, on C plus F,
Mhm.
okay. So let me give you a hint. On C plus F, so here's C, here's F, here's your sum. So that sum here should be around -2, and that's your x component. And your y component should be around -1.5. So that's what those should add up to be. Well, what'd you get for, okay, back up. Elise, what do you have for your x component on C?
4.6.
Positive or negative?
Positive.
That's what's wrong. Because look, that's at 195 degrees, which is down here, okay? So since that's 195 degrees, you're going to have a negative x and a negative y. That's where the wheels fell off. Okay. Now are we good?
Yeah.
Okay, all right, fantastic. All right, so as you prepare for your test, okay? So I might give you something like this. Go, here's a velocity time graph. Okay? And then I might say, okay, okay? So I might say, okay, here's the velocity time graph, okay? So, Elise, here's your velocity time graph. What's the slope of a velocity time graph give you?
Acceleration.
Acceleration. You say you got meters per second divided by seconds. It's going to be meters per second squared, okay? So, Elise, is this a positive slope or a negative slope?
Positive.
Okay, so I have positive acceleration and positive velocity. That means I have to be speeding up, okay? So, and there is no exceptions to this rule, none. Make sure that you go back, and I sent you out like that big packet of notes at the beginning on position time graphs and velocity time graphs. I beg of you, go back and reread through those notes, okay? Start to finish, okay? Make notes, highlight stuff, be an active participant in that reading. So, anytime, and there's no exceptions to this, if your acceleration and your velocity have the same sign, you're speeding up. Okay, that's it. Now, here's the one thing I want you to get out of your mind. I don't want you to look at this and go, oh, they're going forward because they have positive velocity. You don't know which direction that they're headed. You don't know if they're starting at the reference point. You don't know where they are. The only thing that you know about this situation is that they have a positive velocity vector, okay? And it is going in a particular direction. That is all you know, okay? You don't know which direction that they're going. You don't know anything. The only thing you know is that they're moving with a positive velocity and they're speeding up. Okay, that's the only thing that you know. Okay, because this is just a velocity time graph. Now, this is what we call the lip curve or the football curve if you're a sports fan. Okay? So it either looks like lips or it looks like football, depending upon your perspective. Now, Grace. God, why don't you call you Grace? Elise. Which of these curves, A, B, or C, matches this line?
C.
Why?
It's speeding up.
Okay, now, this is a position time graph, right? So what does the slope of a position time graph give you?
Velocity.
So if you have a straight sloping line on a position time graph, the slope is constant, right? If the slope is constant, therefore the velocity is constant, right? So it can't be B, and here's the reason why. Because with B, this is showing a constant velocity. If B was actually what was happening, your velocity time graph would be a horizontal line. Can't be B. Okay? That leaves A or C.
I said C.
Huh?
I said C.
Oh, I thought you said B.
Mm-mm.
I'm sorry. I thought you said B. I'm sorry. Okay, mass. I thought you said B. Yeah, it is C. My apologies, it is C. Okay. So, you got this. This line is becoming steeper. That's going to correspond with this. Now, A would indicate that this thing is slowing down because of the fact that the slope is becoming less shallow. Okay. Now, remember on a velocity time graph, if you were to find this area, that would represent your displacement. Okay? All right. So what I'm going to do, I'm going to tell you right now how this is going to play out. I'm going to give you a position time graph. And let's say that that's 2 meters, 4 meters, 6 meters. Okay? Let's say there's 10 seconds and there's 2 seconds and there's... Okay. So, I'm going to give you a position time graph like this, okay? And I'm going to say, here's some things that I could ask. Is that I might say, all right, I'm going to pick a point. I'm going to say, okay, here's 6 seconds. And I'm going to say, what's the instantaneous velocity at 6 seconds? Okay, so I'm going to give you a designated point in time. I'm going to pick a point and I'm going to say, find the velocity. Now, because this is a curved line, I just can't find the slope of the line. So I'm going to have to draw a tangent line. So remember, on a tangent line, imagine that that's like part of a circle. So you're going to come in here and you're going to take a ruler and you're going to come up to that 6 second mark. You're going to find that line and you're going to draw a tangent line at that point. So if you hand in this test and you haven't drawn a tangent line to a curve, you've done something wrong, okay? So that tangent line is going to go something like, in this particular case, it's going to be something like this. And then you've got to pick 2 points, count them, 2 points on that line to find the slope. You can't just base it on this intersection of this point. You have to pick 2 points on the line. You all did this on the roller coaster sheet, okay, which you have back all your assignments. Go back, look at that roller coaster assignment. I promise you, you're going to do something like this. I might ask you, how many times did it change direction? Oh, every time that slope changes sign, that's going to change direction. So this would have like 1 direction change because that's when the slope changes sign. I might say calculate the average velocity. Now, your average velocity calculation, and this came off that very first lab with the cart, okay, is your overall final position minus your initial position divided by time. So I'm going to pick a time interval, and I'm going to say calculate the average velocity. So let's say that I want the average velocity for this entire trip. Okay, I want the average velocity for the entire trip. Okay, my overall final position is going to be 0. My initial position is, say, 2 meters. And then I'm going to divide that by, say, 12 seconds. Okay? So my overall average velocity, you can take 0 your overall final position over that interval, minus your initial position over that interval, divided by however much time was involved in that. Okay? Average velocity. Overall final position minus initial position divided by your time. So this would be like -1/6 and whatever that is as a fraction. Okay? I'm going to ask you something like this. And then I might say, okay, at the 2-second mark, were you going faster or slower than you were before? So all you have to do is look at the slope. It's like, oh, well, at 2 seconds I'm going faster because the line became steeper. Or I might say after 4 seconds, what happened? Oh, I slowed down because the line became more shallow. Okay? So this is the type of thing you're going to have to do. Now, if I gave you like a velocity time graph, and I said, okay, so this is the velocity time graph, there's 0 meters per second, okay? So, remember, on a velocity time graph, if you're going to change direction, at least what are the 3 things you have to do to change direction?
Slow down, stop, speed back up.
Neutral. You got to do 3 things. You got to slow down, stop, speed back up. So like if I take this golf ball, Gary the golf ball, and I throw Gary up in the air, Gary's going to change direction. So on the way up, the velocity vectors are getting smaller. So here's Gary. So on his way up, the velocity vectors are getting smaller. Okay, they're pointing up, but they're becoming smaller. So that means my acceleration vectors are pointing in the opposite direction. So remember, velocity and acceleration have opposite signs when you slow down. They have same signs when you speed up. Now, on the way down, the velocity vectors are getting bigger. So now I have negative velocity, and now I have negative acceleration, so now I'm speeding up. So this is what's happening when you change direction. So that golf ball changes direction. So it's slowing down on the way up because you have positive velocity and negative acceleration. On the way down, I still have negative acceleration, but now I have negative velocity, and now I'm speeding up. Okay? So that's what you have to be able to think through. So that's what's happening here. So from here to here, if I gave you a velocity time graph and say, hey, you know, indicate if it's speeding up or slowing down, you would say, okay, well, it's speeding up here because, and there's 2 ways you can think about this. One is that you go, okay, well, I have positive velocity and positive acceleration, and I'm speeding up. Here I have positive velocity and negative acceleration, and I'm slowing down. Okay, so some people like to look at it in terms of sign. Some people like to look at it in terms of, oh, here's 0 meters per second. Okay, well, if this is 0 meters per second, if I'm going away from 0 meters per second, I'm speeding up. If I'm going towards 0 meters per second, I'm slowing down. Now, this is not the reference point. Okay, this is not a position time graph. So don't look at this and go, oh, I'm going away from the reference point and then I'm coming back towards the reference point. You have to keep straight the difference between position time graphs and velocity time graphs. Okay, so here's the deal. So from here to here, this is like this golf ball going up in the air. So it's slowing down. It reaches 0 meters per second, and then we change direction because my velocity changes sign. So now I'm going to start to speed back up. Now, do not, here's a very, very common mistake that's made. Elise, did this thing change direction up there?
No,
Why not?
because it just slowed down.
Beautiful. Okay, if I give you this question on the test, I said true or false. If the slope of a velocity time graph changes sign, the object changes direction. Okay, that's categorically false. Because here I've got positive acceleration, here I have negative acceleration. but I didn't change direction because of the fact that my velocity didn't cross 0 meters per second. So if the slope of a velocity time graph changes sign, that just means that you either went from speeding up to slowing down or slowing down to speeding up. Okay? You didn't change direction. The only time you change direction on a velocity time graph is when that line crosses through 0 meters per second. Okay? So keep that straight. So you're speeding up, you start to slow down, here you change direction. So if I were like to act this out, I'd be moving, okay, then I'm going to speed up. Oh my goodness, it's running low. Hold on, I gotta charge my phone. Ah. Okay, we'll let that charge in just a second. Good news is it charges up really fast. Okay. So if I were to act this out, I'd be moving, I'm going to speed up, I'm going to slow down, and then I'm going to change direction. So I was moving, I sped up, I slowed down, I changed direction, I sped back up. Now at least what's happening in this part of the graph? What am I doing?
Just going the same speed.
Yeah. Okay, my velocity isn't changing. There is no acceleration because that's a horizontal line. And then I start to slow down, I change direction again, and then I eventually come to a stop. So I'd be moving in one direction, speed up, oh, slow down, change direction, move at a constant velocity, and then stop again. So those are all the things that you've got to be able to figure out from the perspective of a velocity time graph. Now, Elise, if I were to ask you to find this area underneath here, what does the area under a velocity time graph give you?
Displacement.
Displacement. Okay, now, so that's the type of thing that you got to be able to do. Here's the other thing. I promise you, you have that lab back with the cart, okay, where the cart rolled in and it hit and then it bounced back. I promise you I'm going to ask you questions about that lab. So, let me get my pencil, hopefully it's charged up enough where I can draw. I don't have much to do, so it doesn't have to last much longer. So, here's this cart, okay? It's got the plunger, right? It's going to roll along, hit, boom, and it's going to bounce back. So, that velocity time graph might look something like this, okay? Or if you change how you define positive or negative, it might look something like this. Now, here's the question. If I gave you either one of these velocity time graphs, and I said, where is their maximum acceleration? Okay? You have to get out of your minds that acceleration is just speeding up. Okay? Acceleration is just a rate of change in your velocity. So if I gave you either one of these graphs and said, hey, where's your maximum acceleration? That maximum acceleration is going to occur at the steepest part of that curve. So don't look at this and go, oh, I'm only accelerating here because that's what I'm speeding up because I'm going away from 0 meters per second. No. That maximum acceleration is going to occur across this entire segment here. Your maximum acceleration here would be taking place. Okay? So wherever there's the steepest part of the graph, it doesn't make any difference if it's making you speed up, slow down, it doesn't make any difference. Your maximum acceleration is going to be the steepest part of that graph. Now, let's talk about what makes things change. So, when I did this lab, obviously I did it like this with the wheels down, okay? If I tried to do it like this with the surface here, it wouldn't go very far, okay? Because you'd have a lot of friction. So, remember, friction always acts in the opposite direction of motion. So if I gave you this graph and said, okay, hey, what's making this thing slow down? Well, the only thing that can make this thing slow down as it's rolling is friction. Oh, okay. I had a little bit of friction, and it's making it slow down, okay? And that's why that's approaching 0 meters per second. Now, at this point, bam, I hit the wall. That's when that plunger begins to compress like this, okay? So my plunger is compressing. That's what's happening in this part. This is when I fully stopped. This is when that plunger is pushing back and it's making it speed up. And then it's rolling and friction is making it slow down. So here and here, this is where friction is making it slow down. This is when the plunger is in contact with the wall. So that's what you've got to be able to do, is take a velocity time graph like this and figure out, okay, hey, what's taking place? So here's your overall theme. Is that F equals ma. Mass is always positive. So here, I've got a little bit of positive acceleration, which means that I would have a positive force, but it's acting in the opposite direction because I have negative velocity. So what would physically be happening with this cart is that that cart would be moving with a negative velocity. My frictional force, a little bit of it, would be acting in the opposite direction, and that's what's making it slow down. All of a sudden, bam, I hit the plunger. Now I get a big positive force. I get a big positive acceleration. That's what's making it really slow down because of the spring. Then the spring expands, bam, pushes it in the opposite direction. I speed up. Then I'm rolling again with friction, but now I have positive velocity. So now the cart is going in this direction. My acceleration and my frictional force is in the opposite direction, and that's what's making it slow down. So that's the other thing that you've got. Okay, so those are the big ideas. And so what I'm going to send out to all of you, and I got Grace's. So let me kind of take you through what you're going to get. So you're going to get this list of topics that are going to be covered on the test, okay, which is basically everything that we went through here. Your terminology, frame of reference, reference point, position, displacement, velocity. Understand the difference between like distance and displacement, speed versus velocity, okay? Understand the difference between the two of them. You're going to get hammered on position time graphs and velocity time graphs, okay? I'm going to tell you that right now. Now, here's the other big equation that you're going to have on that you should realize, is that distance equals velocity times time, okay? So like on assignment 2-1, you all did a bunch of calculations with this. Here's for whatever reason, the biggest struggle is if I ask you to find time. And for whatever reason, you try and take velocity and divide it by distance to try and find time, okay? Okay, you can't do this for any number of reasons. Number one, just look at the units. You got meters per second divided by meters. Meters cancel out, but you get 1/seconds, okay? 1/seconds is not seconds. You just can't wish it upon yourself and go, oh, I'll just act like that's seconds. No, you're getting the inverse of time. But what happens is that if you take distance and divide it by velocity, so that's meters times the inverse of velocity, which is seconds over meters, then you get seconds. So again, if you get done with the test and you haven't used the idea that distance equals velocity times time, you've done something wrong. Okay? I'm going to tell you that right now. Displacement equals velocity times time. Promise you there's going to be at least 2 questions on there like that. Promise you. Okay. The vector addition, I told you there's going to be the 3 problems like that. One where you draw them out, one where you find the components, one where you add them all together. Okay. So and this is what I'm going to do with every test from here on out. So here's 6 questions. No, this is not due because I'm giving you the answer key to it. So, and if you do this, great. If you don't, hey, that's up to you. But this is what I have found myself. when I was studying for a test, whether it's a math test or physics or chemistry, and this is basically a math test to a certain extent. Physics and upper level chemistry is basically a math class that we call physics and chemistry. And we get Cooper tools. So what I would do, if I were you all, this is what I would do if I was preparing for this test. I would take this and I would treat it like the test. I wouldn't even look at that answer key, okay? Wouldn't even look at it. I would try and work every problem on here. Then, when I get done, then I'd go look at this and see how I did. Because here's the problem. If you look at what I did first, you're automatically biased, okay? Because if you read what I wrote from the answer to number 1, and then you read question number 1, and then it's like, oh yeah, Burkamp got that one right. Oh, cool, he's 1 for 1, okay? No. Now, if you don't have a clue, like let's say for example, you read a problem and you don't have a clue how to even start the problem, then you can look at what I did. But that's going to tell you that, wow, I don't know how to do this particular type of problem. I would go back and I would look at your old assignments, which you all have back. If you've missed anything, figure out what went wrong, work those problems again. If you have the time, you could take this one and rework the problems, but change the numbers a little bit, change the angles, change the magnitudes of stuff, okay? And see how that plays out. Draw your own position time graph, draw your own velocity time graph, think that through. If nothing else, and this is what I would do, especially after I taught for a while when I would take a physics class, is that I would write my own test, okay? I say, okay, if I were writing the test, how would I approach this question, okay? And then I'd make up my own questions and I'd work them. So that's not a bad approach to have either. And it isn't just physics, it's any topic. Say, okay, if I were to write the test, what would I emphasize? How would I write that question? Would I make it a multiple choice question? Would I make it a true-false question? Would I make the kids work it out? So that's actually an effective way to study, is say, hey, I'm going to write my own test. I'm going to give it to Burkamp. What would I ask Burkamp about these questions and how would I ask it? So that's a possibility. This boils down to repetition, okay? If you're going to play basketball, you're not going to shoot one layup and make it and go, okay, hey, I'm done. I don't have to shoot any more layups. Same thing is going to happen with these problems. You need to work these problems again and again and again until you feel absolutely comfortable with it. And then you change the numbers and then you work the problems again. So that's my advice. So you're going to get this, which is a set of questions, and then you're going to get this, which is the answer key to that, and then you're going to get this, which is the list of things that you need to know for the test. So you have everything back. If you need to hand in this last assignment, I'll get that graded as soon as possible, and then I'll get that back to you so you have that to study for the test. Okay, Elise and I are done showing out. I'm going to give you the review. You all have a wonderful, safe weekend. Stay warm, and be thankful you don't live in Texas. So, there we go.